Hey everyone, it's raining behind me, which is wonderful. Should signal an end to this smoke. I wanted to just talk a little bit about magnetic fields created by current carrying wires, a little bit more of a quantitative way than we've talked about before. So we saw that the magnetic field created by a wire with current running through it is circular around that wire. Over here in the top left, we have a side view of that, similar to the one we've drawn in class. And with our new sort of vector representation, we can also draw a top view with a wire coming out of the board, or with a wire current coming out of the board. And we can see the shape of the magnetic field created by that. So it stands to reason that the magnetic field created by a wire should increase with current. If you double the current, it should double the magnetic field created by it. It also makes sense that the magnetic field should fall off with distance. Magnetic field can't possibly stay the same strength no matter how far away you get from the wire. It should fall off with distance in some way. And experimentally, the way that it falls off with distance is found to be as 1 over r, rather than the 1 over r squared for a electric charge, for example. So the magnetic field is proportional to current divided by distance from the wire. And if you add in a constant, you make this an equality instead of just proportionality. And you can find that the magnetic field is equal to this constant mu naught, which we'll get to in a second, divided by 2 pi, times the current running through the wire divided by the distance from the wire. And this is pretty specific to a long straight wire. If your wire is in some other shape, you have to be a little bit more clever to figure out the electric field strength near that wire. And we'll get to that in just a little bit. And the direction of this magnetic field is given by the right-hand rule. And we went through this previously, but to apply the right-hand rule for a long straight wire, you put your thumb in the direction of the current, and you wrap your fingers around an imaginary wire. And the direction that your fingers curl gives you the direction of the magnetic field tangential to a circle, a radius r, around that wire. Now this constant mu naught, which should not be confused with either the magnetic dipole moment nor our electric constant, epsilon naught. This constant mu naught is the magnetic constant, also known as the permeability of free space. Essentially tells us how well magnetic fields are able to propagate through free space. And the value of mu naught is 4 pi times 10 to the minus 7th Tesla meters per amp. You'll notice this is a little bit strange among constants in that it has pi in it. And that's because until actually just about last week, this constant was exact. And the Coulomb, and therefore the amp, were actually defined based on the permeability of free space, this magnetic constant. It's actually changed in the last week since it was voted to change the definitions of various SI units. I recommend reading up on that, it's really interesting. So just like electric fields, magnetic fields are vectors. And if you have multiple sources of magnetic field, creating magnetic field at a single point, those magnetic fields add up like vectors. This is again the principle of superposition. So as an example, let's say that we have 2 long straight wires. One of them has a current of 5.0 amps running through it, coming out of the board, and the other, 10 centimeters away, has a current I2 is 7.0 amps going into the board. And we want to find the magnetic field halfway between the wires, so 5 centimeters from each. Well, to do so, we can find the magnetic field created by each of these wires individually, and then add them up as vectors. So to find the magnetic field created by the 5 amp current, we can sort of sketch in a circle 5 centimeters away. And we know that the magnetic field is going to be tangential to that circle at all points. So at a point exactly halfway between these wires, there's sort of 2 options for the direction of that magnetic field. It could be up or it could be down. And to work out which it is, we can again use the right-hand rule. We can take our right hand, we can put it this, so that our thumb faces out of the paper, or out of the screen in this case, and wrap our fingers around that imaginary wire. And we can see that, it's a little hard to see here, we can see that here, over to the right of the wire, our finger is going to point up. And so the magnetic field created by that current will be pointing up at that point, or in the positive y direction with the coordinate system that we've established here. We can do the same thing for the current pointing into the board. We know that it's going to be tangential to the circle, 5 centimeters away from it. And so at the points midway between the two currents, it has sort of two options. It can be up in the positive y direction, or it can be down in the negative y direction. And we can use the right-hand rule to figure out that it will in fact be up. So we can draw in our two vectors. We can start out with these directions for these vectors. And then we can figure out their strengths. So B1, the magnetic field created by current 1, that 5 amp current, is mu naught over 2 pi times current 1 over the distance from that current. We can plug in mu naught, which is 4 pi times 10 to the minus 7th Tesla meters per amp. We can plug in our current, 5 amps, and 2 pi, and the distance to that point, which is 5 centimeters, which I've just written in meters. And we get that magnetic field 1 is 2.0 times 10 to the minus 5th Tesla. And the magnetic field created by current 2 can be, or the, I should say, magnitude of the magnetic field created by current 2 can be found in much the same way. And because both of these magnetic fields point in the same direction, their amplitudes are just directly going to add. And so the amplitude of the total magnetic field is going to be B1 plus B2, the magnetic field created by current 1 plus the magnetic field created by current 2. And so the total magnitude is going to be 4.8 times 10 to the minus 5th Tesla in direction plus y. You will certainly have more complicated problems than this that will involve vector addition, but we know how to do that because we've worked with electric fields so much. So current carrying wires will produce magnetic field. They'll also feel a force from magnetic field. And so if you put two current carrying wires near one another, they'll exert a force on one another. Let's say that we have two current carrying wires arranged like this. One of them has a current I1 traveling in an upward, pointed in an upward direction through it, and a distance d away is a second wire with a current I2 running through it. We want to find the force between the wires. So the thing we can do first is find the magnetic field at the second wire, current I2 running through it, created by current I1. So first we can find the direction of that magnetic field. We can find that direction using the right-hand rule. So current I1 is pointing upward, and so we can curl our fingers around that imaginary wire, and we know that the magnetic field is going to be tangential to a circle, a distance d away. So that leaves sort of two options of which way the magnetic field can be pointing at I2, either into the board or out of the board. And the right-hand rule tells us that our fingers are curling this way, which is into the board. So the magnetic field created by current 1 at current 2 is going to be pointing into the board. It's going to have a strength of mu naught over 2 pi times current 1 over d, the distance between the two. The force is going to be ILB sine theta. The angle between the magnetic field and current 2 is 90 degrees, so sine of theta is 1. So the force on wire 2 will be current 2 times the length of wire 2 that's within that magnetic field, which should be the entire length of it, times magnetic field created by current 1 at wire 2. And if we plug those things in, we get that the force is mu naught over 2 pi times the product of the currents times the length of wire 2 divided by the distance between them. Now it's often much more useful to think about force per unit length, since very often we have very long wires, and thinking about the total force on them is not terribly useful, but thinking about the force per unit length can be quite useful. And so we can divide that force by the length of one of the wires, which should be the length of both wires, to get that the force per unit length is mu naught over 2 pi times the product of the currents divided by the distance between them. It should also be noted that the direction of this force can be found by the right-hand rule. Again, the version of the right-hand rule that applies here has the index finger in the direction of the current, the rest of your fingers in the direction of the magnetic field, and then your thumb gives you the direction of the force. So the force on current 2 due to current 1 is to the left. And we can do just the same thing to figure out the magnitude and direction of the force on current 1 due to current 2. We don't really need to, because we have Newton's third law, which tells us that whenever one object exerts a force on another, the second object exerts a force back on the first with the same magnitude in the opposite direction. So we know that the force on current 1 due to current 2 is going to have the same magnitude, but it's going to be in the opposite direction. So these two current carrying wires attract one another, these two current carrying wires with current pointing in the same direction. If we reverse the direction of the current through one of them, it would reverse the direction of the magnetic field created by that wire. And then the other wire would feel a force in the opposite direction. And so what we find is that if currents in two parallel current carrying wires are in the same direction, they're going to attract each other. The force is going to be inward. But if the currents are in opposite directions, they're going to repel each other, and the force is going to be in opposite directions.